Now that we've learned how to integrate scalar fields over surfaces, let's talk about how to integrate vector fields over surfaces. The motivation to calculate a surface integral of a vector field is to calculate what's called the flux of the vector field through the surface. Let's review the notion of flux. So the context here would be that the vector field we're studying measures maybe the velocity of a fluid flow in space. So the units for the vector field here might be meters per second. So what we have is a fluid flow represented by a vector field flowing through a surface. So in our picture here, we're looking at a surface, and let's say we look at a particular point on the surface. The idea is that this vector, the vector field, represents fluid flowing across the surface at that point. Flux is measured in meters cubed per second, and what flux measures is the rate at which fluid volume flows through the surface. So flux is a rate at which the volume of the fluid in question is passing through the surface. So how do we get our hands on flux? Well, let's look and see what the density would be in this context. We define flux density at a point through the standard normal vector to be the component of the vector field along the standard normal vector. So here, if we calculate the standard normal vector for our surface, our parametrization of the surface, we can calculate the component of the vector field in the direction of this normal vector. And the idea is that this component gives us what's called flux density at every point on the surface. So let's now think of a generic example. Let's say we're studying a surface S in 3 dimensions. And let's say we're in the presence of a vector field that models fluid flow at every point on the surface. So we have a bunch of points on the surface, and we have a vector field that's modeling the way that fluid is flowing across the surface at every point. So the next type of integral we're about to define is called the vector surface integral of our vector field over our parametrized surface. So before we give the precise mathematical definition, I want to state the purpose of this integral. So the notation we're about to introduce is the double integral over the parametrization of the surface of the vector field dotted with the symbol d vector s. And the purpose of this new type of integral is to calculate the flux of the vector field through the surface. The idea here is that if the fluid flow is measured as a velocity in meters per second, the flux, since it measures the volume, the rate at which a volume of liquid or fluid is flowing through the surface, should have units meters cubed per second, or volume units per second. Okay, so now let's look at the precise mathematical definition of a vector surface integral. The vector surface integral of a vector field f along a parametrized surface, bold x, again is defined symbolically as 2 integrals over the parametrization of the dot product of f with this new symbol d bold s. And this is defined as the double integral, so this is an ordinary double integral, over the domain of the parametrization for the surface, d, of the vector field applied to the parametrization, dotted with the standard normal for the parametrization, dA. So to calculate a vector surface integral, we apply the vector field to the parametrization, and we dot with the standard normal vector, and then we integrate over the domain of the parametrization. Here we're introducing new notation. When we write d bold s, what we are referring to is the standard normal vector multiplied by dA. So here on the left, we're introducing the symbol d bold s, and that's meant to stand in for the standard normal vector n multiplied by dA here on the right. And again, if we track the units in this definition, we can once again interpret the scalar surface, or the vector surface integral. So here, the units on the vector field f are the units of flow velocity, and the units of the standard normal vector we saw before are area units in the surface divided by area units over the domain of the parametrization. And when we multiply by dA here, the idea is that since we're taking a double integral over the domain of the parametrization, the units on dA should be area units in D. When we multiply all these together, the D area units cancel out, and we end up taking the flow velocity and multiplying by area units in the surface. This is exactly how flux works. We take flow velocity and multiply by area in the surface. We can also interpret our vector surface integrals by rewriting the integral and reinterpreting. So instead of looking at f applied to the parametrization and dotting with the standard normal, one thing we can do is we can multiply by 1 here by dividing the standard normal by its length and then multiplying by its length. One interesting thing that pops out here is that what we're looking at now is f applied to the parametrization multiplied by the normalization of the standard normal vector. That's exactly the component of the vector field in the direction of the standard normal. And then now we're integrating the length of the standard normal vector dA, which is previously how we defined d capital S. So we can sort of view the vector surface integral as an ordinary surface integral where the density function is flux density, which is how we defined the component of f along n, which would tell us that the vector surface integral is designed to calculate flux. Okay, so let's now do some examples. So let's go back to our example where S was the first octant part of our plane 4x plus 2y plus z equals 12. So we saw previously how to visualize this surface by figuring out where the plane crosses each of our 3 coordinate axes. To figure out how to parametrize this surface, we noticed that the surface was defined over a 2-dimensional region in the xy plane, and that 2-dimensional region is a triangle with vertices origin, 3, 0, and 0, 6. And to parametrize, we kept x and y equal to themselves, and then we set z equal to the appropriate expression needed to force the equation of the plane to work. In this case, we need to set z equal to 12 minus 4x minus 2y. Once we have our parametrization for our surface, we calculate the 2 tangent vectors, which we found previously to be 1, 0, negative 4, and 0, 1, negative 2. And then we take the cross product of those 2 tangent vectors to find the standard normal vector, which we found to be 4, 2, 1. Now, let's look at a particular vector field. Let's look at the vector field f equals z, 1, negative 2. And let's say that this vector field is measuring a fluid velocity in space. So here the units on the vector field are meters per second. Well, let's now calculate the flux of this vector field across the surface, which is calculated with our vector surface integral, double integral over the parametrization of the vector field dotted with d vector s. And this notation, it stands in for the double integral over the domain of the parametrization of the dot product of f applied to the parametrization with the standard normal vector. So this term in red here is meant to represent the vector field where we're applying the vector field to the parametrization. So we are replacing any z's in this vector field with the expression 12 minus 4x minus 2y, which is why z1 negative 2 becomes 12 minus 4x minus 2y, comma 1, comma negative 2. Then we dot with the standard normal vector, which we calculated to be 4, 2, 1. And now we're integrating dy dx, because I'm choosing to use x slicing throughout this domain in the xy plane. So now I can take my dot product by taking the first entry inside of f, which is 12 minus 4x minus 2y. I multiply by 4. Then I add 1 multiplied by 2. And then we add negative 2 multiplied by 1. And now I have an ordinary double integral dy dx. And when I do the calculus here, I end up with 144 as a scalar quantity. And since the original vector field was measuring fluid flow in meters per second, the flux, which represents the rate at which volume is crossing this surface, has units meters cubed per second. So the idea is that if we let this fluid flow for 1 second according to this vector field's a description of the velocity, 144 meters cubed a volume worth of fluid would cross over this surface. Let's do one more example. So let's say that S here is the unit sphere, and let's say that the vector field representing fluid flow is given by the vector field 1, 2, z. And here again, the fluid flow is measured in meters per second. So here we're working with the unit sphere. Well, to parametrize the unit sphere, we can take advantage of the idea of spherical coordinates. The idea is that if we simply write down spherical coordinates where the variables are phi and theta and set rho equal to 1, we get exactly a parametrization of the unit sphere. We can then proceed to, so the idea is that we're setting x equal to cosine theta sine phi, we're setting y equal to sine theta sine phi, and we're setting z equal to cosine phi here. We can then proceed to calculate our tangent vectors. We calculate our first tangent vector by differentiating every coordinate with respect to phi. So in this case, the first coordinate with respect to phi takes sine to cosine, so we get cosine theta cosine phi. When we differentiate the second coordinate with respect to phi, we get cosine phi sine theta. And when we differentiate our last coordinate with respect to phi, we get negative sine phi. Then we can calculate our second tangent vector by differentiating each of x, y, and z with respect to theta. This should give us negative sine theta times sine phi. Then we should get cosine theta sine phi, and then we should get 0. The standard normal vector is obtained by taking the cross product of these two tangent vectors. And when I took that cross product, I got first coordinate as cosine theta sine squared phi, sine theta sine squared phi, and then cosine phi times sine phi. So now we have all the data necessary for calculating the flux in this scenario. The flux of our vector field through this surface is notationally referred to as double integral over the parametrization of the dot product of the vector field with d vector s. And this is meant to stand in place for the double integral over the domain of the parametrization of the dot product of the vector field, where we replace all of the x's, y's, and z's with the appropriate phis and thetas, and then we take a dot product with the standard normal vector that we just calculated. So in our vector field, the formula was 1, 2, z, so we need to replace our z with the cosine of phi, and then we take a dot product of that vector field with the standard normal vector, which we previously calculated. When we do the dot product here, we should get 1 multiplied by the first coordinate of our standard normal, which is cosine theta sine squared phi. Then the next term should be 2 multiplied by the second coordinate of the standard normal, sine theta sine squared phi. And then for the third term, we take the third coordinate of the vector field, cosine of phi, and multiply by the third coordinate of the standard normal, cosine phi sine phi. Remember that for spherical coordinates, the thetas and phis range from 0 to 2 pi and 0 to pi. So now I'm going to integrate this whole expression, d phi d theta, from phi equals 0 to phi equals pi, and theta equals 0 to theta equals 2 pi. When I did the calculation here, I got 4/3 pi, and the units on flux in this scenario should again be meters cubed per second, because the flux represents the rate at which the volume of fluid is flowing across the surface. Here, the velocity was measured in meters per second.